most n-bit strings are algorithmically incompressible. You know, they're algorithmically random. But what omega is an infinite sequence where every initial segment is essentially algorithmically incompressible, algorithmically random. That's the point. To have one sequence where wherever you cut it off, what you get is incompressible. It will not be, in fact, just at random, the complexity will dip down a little bit. You know, if you look at the nth bit, the size in bits of the program you need, the smallest program you need to calculate the first n bits of omega, will always be greater than n minus c if you're calculating in bits. But it turns out that the highest possible complexity you can get for an n-bit, in fact, most n-bit strings have higher complexity. They have n plus h of n. It's the number of bits you need to calculate in the minimum size program to calculate n. In fact, you can show within that's the. And this is roughly of order n plus log n. So in fact, the initial bits of omega, the fact that you're getting this all out of one sequence does force the complexities to be a little lower. But this is just probability theory, because it turns out that just at random, the complexity will have to dip infinitely often, that far in an infinite sequence. Why? Well, there are different proofs, but the one I found as a teenager, so that one is dear to my heart. There were more sophisticated technical proofs now by lots of people, but the one that I found as a teenager, which is close to my heart, is very simple. I was reading that wonderful book on probability theory by Feller, which at least was the book that a whole generation of students, including myself, learned probability theory from. It's a wonderful book. And he has exercises talking about how long, if you have independent tosses of a fair coin, he has some exercises where you calculate how long you will get runs of heads or runs of tails. And it all has to do with, it's exactly this calculation just like this, having to do with, you can show that infinitely often in the first n bits of an infinite sequence of independent tosses of a fair coin, you're going to get a run of log 2n bits of that are all the same. This will happen with probability 1. Is it log 2n bits? I think so. It's basically just this same question of whether this converges or diverges. If it converges, you're only going to get it. This does converge. Okay, if this converges, so only finitely often you will get a run this big in the first k bits, a run of that many heads or tails in a row, or zeros and ones. But if it diverges, then infinitely often you will, and it does diverge if you take off the self-limiting part, and you just have this, infinitely often you're going to get a run of more than this number of bits identical in the first k bits. So this is really basic probability theory. And so just because in an infinite random sequence you are likely to get long runs, the runs will be this long of bits that are the same, then the complexity will have to dip because a lot of the bits are the same. You can shrink the size of the program that calculates this sequence if you're truncating the sequence just where you end with a long run of bits that are the same. So that you can basically compress that long run of identical bits out. So that's an easy way to see that infinitely often the complexity will have to dip. And maybe I'm telling you more algorithmic information theory you want to know. But anyway, so anyway, this is basically it, and I want to thank you for your patience. I'm sure I've run way over the time. I won't even look. Do we have time for questions or comments? Or thanks very much for your patience.
Okay, now it's time for some questions.
Okay, I have two questions. The first one is, does this rate of evolution with n squared and so on depends on the fitness criteria you choose? I mean,
Absolutely.
Okay.
Sure. I mean, as you point out in your paper, when you explain all this so nicely, a model of this kind is a triple. You are choosing a programming language, which is the language of your organisms, your software organisms. You are choosing a fitness measure, and what's the third thing? Ah, yes, of course. How could I forget? You have to decide what your mutations are and with what probabilities. And anytime you change one of those things, you get different behavior. So this is one model where I can characterize the behavior. But it happens to be a model that, at least if you have my mathematical background, looks natural. Okay? Not to a biologist, obviously. But what I'm doing is I'm trying to create a new field of mathematics more than anything else. A new field of mathematics that is inspired by biology. Then if we're very lucky and more people work on this for years, maybe we can go back to biology and say something that is of interest to biologists. Yeah, so if you change things, it all falls apart.
Okay, so and the second question is related to that. So can you translate these results to something that you can compare with biological
Are you a
systems?
biologist?
No, I'm not. I'm a physicist too.
Okay, great.
But anyway.
Yeah, I tried to discuss this yesterday.
Yeah. So you can compare.
According to my beloved wife Virginia, I covered my face with egg, as they say in the United States. Maybe an expression you don't know. So I don't dare to repeat what I said yesterday because she'll beat me to a pulp. Well, I attempted to do that. Yes, shall I repeat the...
No.
Okay. It's questionable how you can, whether these estimates tell you anything about the rate of real biological evolution. First of all, in real biology, there are no oracles. You don't have mutations this incredibly powerful. They may be powerful, if Maximo Sandin is correct, and they're viruses, but this is very powerful. And then the purpose of real biological evolution is not to calculate lower bounds on the halting probability, right, or do well in the Busy-Bieber problem. That's a mathematical challenge. You know, they have other challenges here. The creativity springs from the Red Queen hypothesis, supposedly. Also, the notion of time, the measure of time I'm using here is very strange. It has nothing to do with, shall we say, physical time, or even with compute time. My measure of time is how many mutations did I try. Now notice that the mutations mk, my beloved mutations m sub k, they are a really horrendous computation that would take a monstrous amount of time. This is very theoretical, abstract mathematics. So I think it's a real question for further research to see if this has any connection at all with real biology, or to make changes in these models, going in the direction of models which, yes, do have a connection with biology, and to see how well there's a match. Because you might go to biology, you might get models that are closer to biology and that you can compare with what happens in biology, and you might find that the behavior of the models really, you can show, is different from the behavior of the way evolution works if you're doing in vitro evolution, say, of bacteria or something. And in that case, you know, you would have an experimental proof that Darwin's theory is wrong. Now, this shouldn't come as a surprise to anybody. The book by Mauricio Abdala that I waved here, I think, the first day, he's a Brazilian who couldn't publish it in Portuguese in Brazil because he criticizes Darwin. It's a wonderful book. He's a philosopher. It's published here in Spanish. I just picked it up here in Madrid a few days ago. And he talks about three basic kinds of criticism of Darwin's theory, technical criticisms. One, Behe, I don't know, B-E-H-E, saying that some things in biology look irreducibly complicated. Darwin didn't know that cells are so incredibly complicated. Cells are so monstrosly complicated. Not only they're complicated, they're parts which look like you can't get them from anything simpler. If you remove anything, it's useless. That's irreducible complexity. Then the other objections he discusses are really from somebody called Lynn Margulis. This was the wife of Sagan, and she is actually a better scientist than he is. Americans love examples like this, right? So she's the biologist who's responsible for showing that symbiosis is a tremendously important driving force in biology, because she convinced biologists, you know, in retrospect it looks the evidence is very compelling, but you know, you have to convince people what was it? Mitochondria, which are used for energy, production in the cell, they were really separate organisms. And it's, now that we know all the details, it's very easy to see, because they have their own genes that are not part of the main genes of the cell. And these basically is a matriarchal line that you're only, because it goes through the cytoplasm, you're not getting the cytoplasm from the father, you're only getting genetic information, DNA. And it's slightly different, the coding. So So this big step forward, even in single-celled organisms, when you go from the primitive bacteria that don't have a nucleus to the really sophisticated 2 billion years later single-celled organisms are really enormously sophisticated. Somebody was telling me, maybe it's this book that I was reading, and maybe it comes from Maximo, that really single-celled organisms are as sophisticated as we are. It's just they went off in a different direction. And in fact, they have group intelligence because they can pass around useful information, which is why you have superbugs. It's just a different solution to the problem of being alive than us. In their own way, an individual cell is like a city. It's like all of Madrid, one cell in your body. So that's the next objection. And the third line of objection that he said, in fact, is Abdallah in his book, is of course Maximo Sandin, who does more than point out that there are holes apparently in the match from Darwin's theory to the experimental data now. He actually proposes a complete replacement. And part of this replacement is that evolution is not gradual, and that in fact it's not random mutations that are the main driving force, it's really viruses which are transmitting information horizontally, even in organisms like ourselves. We know that this happens, of course, in single-celled organisms through conjugation. And apparently the evidence is really rather intriguing. Now that people can compare entire genomes, it looks like someone was telling